we'll begin by taking a look at the calendar. So today, project number 5 is due, so hopefully you've done some calculations and you can tell me the approximate volumes of lots of different kinds of candy, which will give you that much more of an appreciation when you eat the candy in the future. And now that project number 5 is done, there's no rest for the weary. Here's project 6. So project 6 is due, what does it look like? April the 5th. So I think that's 1 week from today. And the good news is, once you get this project turned in, there's actually a little bit of a gap between project 6 and when project 7 is assigned. There you go. Okay, so I guess that's it. There is a quiz coming up on Wednesday next week, April the 3rd. Also, speaking of next week, what's happening on Tuesday? Advising day. So we've talked about that before. It's more than just a day where there are no day classes. It's a lot of stuff that we are hoping we can entice you to come in for. Any questions on the calendar? Okay, one more announcement. If you are interested in maybe taking an online class and you haven't done it before, but you want to kind of get some information about it before you decide whether or not to take the plunge, there is going to be an information session this coming Monday, April the 1st, in the Core 307. It's called the McLeish Room. Pizza will be served, and it will talk to you about, what you can expect from an online course and how it differs from a face-to-face, a traditional course, how much time maybe would be involved in taking an online course. So all of your questions about online courses will be answered. Personally, I have never taken one, but if I were thinking about doing it, I would go to this on Monday. Any questions on that? Okay, yeah, pizza. Right, so then the next thing here, I'm on page 38, but I think we start on 41. But I just want to point out that there is an article that was part of the reading for last night's reading. Where is it? Read the first, write a couple. Oh yeah, write a couple of sentences expressing your thoughts on the Strogatz article. So there's this article that I copied. It's better to go to the link that I've given you there. But I just want to point out, I know it's been very busy with our class and probably your other classes too, but I think this is a wonderful article and it is worth reading. And if you haven't read it, maybe you can take 10 minutes this weekend and read it. If you are able to get online, go to the online version because there's some animations and there's some links and it's better to read it online. But if you don't have access to the internet over the weekend, then certainly it's a very good article to read in paper. Anybody have a chance to read it over the last couple of days? Yeah. So, yeah, and did you find? Yeah, it's kind of an inspirational article, but I'm hoping it also brings together a lot of the ideas that you've studied here this semester. So please check it out if you're able. I'm not going to test you on it or anything, but I think it's worth reading. So if we go to here, page 42 is where we begin today. And it says at the top, Project 6 is assigned. So again, make sure you grab a copy of Project 6. It also says, and you don't have this on yours, that you're going to skip number 14 if you are doing the homework tonight. And the reason you're going to skip it is because essentially I took it and threw it in the project. So it's not like you're avoiding it, just I don't need you to do it twice. So you can cross off number 14 if you're doing tonight's homework. Wonderful. If somebody has a textbook, I really feel like I did assign the question that's in the project, and maybe it's not number 14. So I'll take a look if somebody can open the textbook to tonight's homework. All right, so we'll start with number 1. And can we begin with, let's see, Sam, are you ready? All right, what's the formula for work? Force times distance, yes? Keep going, Sam. Okay, so let's just talk a little bit about work in general. So so it's defined to be how much force you apply times how much distance you carry that thing through. So if I take this water bottle, this is an example from your textbook, and I walk it over here. So I've walked, 2 meters, And have I applied force? The answer is not really. I mean, I kind of feel like I did some work, but I didn't really do work according to the definition, because if I weren't here, what would happen to the water bottle if I just vanished? It would drop. So in terms of the distance that we're moving, it's not in the same direction that gravity is trying to pull this thing, right? So in the horizontal direction, there's no force that I'm applying. But if I lifted this thing, I'd be applying some force against gravity. But in this example, there's no force being applied because there's no horizontal thing that's trying to prevent me from moving. And so there would be no work just by walking this thing left to right. But if I lift it up, now there's work being done because I'm going against another force. Same kind of thing if I try to drag this table over here. I can pull this thing, you know, half a meter, and I've done work. Now that's horizontal, so it's not a work against gravity. What did I work against? The friction. So there's a friction force that the carpet is applying to the table. So there's work being done there. But in order for work to happen, you got to be you have to be opposing some force that's already acting on the object. Okay, so let's go to number 2, and we are back to David. Are you on the right page? Nope. We'll come up here to Chris for number 2. Okay, so here's the basic idea. We got this spring, and in the first picture, the far left picture, it says that equilibrium position is right over here. So normally the spring, if it's at rest, it will be from here to here, right? That's what we mean by equilibrium. So if you try to pull the spring, then you're going to encounter some resistance, and if you try to push the spring, you'll encounter some resistance. Spring wants to be at equilibrium. If we try to do something other than that, it will fight back. So suppose that you are pushing the spring in this way. What's going to happen to the amount of force that will be required to compress it as you compress it? It's going to increase, because the more compressed the spring is, the harder it will be to compress it even further, right? The spring gets angrier and angrier, and so it will push back more and more. And so the formula that we're given in this problem is this guy right here. The force that's required to move this thing is 12 times x, where x is this distance in here. So for example, if we plug in, say, x equals 0.5, then how much force is required at that point? 6 newtons. Newton is the standard unit of force in SI. So 6 newtons of force are required there. If I had the block over to here, and actually this was a distance of 1 meter, it's a very big spring, then how much force is required at that moment? If we plug in x equals 1, we get 12 newtons, okay? So that's how much force is required at any moment in this spring's horizontal plane. So how do we figure out how much work we do? Well, so we're going to compress the spring from where it is to 0.5, from equilibrium to 0.5. Why is it difficult to use this force times distance thing? The force changes. And how often does the force change as we're compressing this half a meter? At every single moment, right? The amount of force required at one moment is different than a millimeter away. And so what we're going to do is essentially chop up that half a meter into millimeters. And we'll just assume that the force required to move the thing over a millimeter doesn't change very much. And then if we think millimeters are too big, we'll chop it down to even smaller things, nanometers, picometers. I don't really know all my stuff. Femtometers. And that's the basic idea. And then what is that going to turn into when I add up all these little tiny slices of work? It'll become an integral. Okay, so let's give it a shot. There's a picture on the far right. It says, suppose that the block is currently here. I'll write that here. So this is the current position for the block. And that is to say, it has already moved x meters. So equilibrium was way back there. So we've already moved it to some generic place. This is like picking a generic slice. And then we're going to move the block a tiny bit. And you can see symbolically what's the length there. Delta x, a little change in x, so it looks familiar. And we're going to ask ourselves how much work is done to move the block that tiny bit. and we're going to use force times distance. And what Chris said is still valid. The force does change as you compress the spring, even that little tiny bit, but if it's small, if it's a small little width, it doesn't change that much. So what it says down here, it says the work done in compressing the spring a small distance is kx delta x. You can cross off the k, that's the generic thing. For us, it's 12. 12x was our formula. So let's see if we can start calculating. So the work done for the little tiny interval. Again, it's the force over the interval times the distance over the interval. Force times distance. Work, yeah. And then how much force is required the moment we're at this position right here, which is position X. I don't know, it's going to have X in it. It's 12X, right? That's the formula. If you are sitting exactly at X, then the formula is 12X. So we're going to assume that for all the little points in here, it's approximately 12X, because we're assuming that's a pretty tiny interval there. So then the force there is approximately 12X times the distance. What is the distance that we're moving it in this little interval? It is what? Delta X, change in X. So that right there is where the 12X delta X comes from. 12X is the force, delta X is the distance. Which one of those two is the reason for the approximately equal to symbol? It's the 12X. It's not really 12X consistently through that interval, but it's an approximation. And so that right there, 12X delta X, is approximately the work done for that little interval. And then we're going to find the work done for all the intervals. What am I going to throw in front of the 12X delta X? Sigma. We're just going to add up the work done for all these little pieces. I'll play my little game where I stick an I that's going to go away. And then when we let the number of little pieces go to infinity, that sigma becomes integral. So for the first time here, I'm going to write the total work, and I'm going to put equals. It's no longer approximate when we send the number of intervals to infinity. So it's equal to 12xi. What does that become? 12x. Delta x becomes dx. And the last thing that we need is the limits of integration. So again, look at how x is defined, and what's the smallest x, and what's the biggest x. 0 and 0.5. 0.5 was in the problem. This is the only place that we use it, but we're going from rest, which is 0, up to 0.5. And that's it. Any questions on getting to that integral? And you know, as usual, like setting up the integral is the interesting part, at least as far as I'm concerned. The calculation is not all that interesting. We'll just put a number here so we can have some units to write down, but let's see, that becomes a 6x squared, and then we're plugging in a 0.5, so we're squaring 0.5, so we get 0.25 times 6. Is that 1.5? Double check me that this is the answer that I get. How long the spring is at rest. So what would you do to determine that? I feel like there are, what's that?
When we substitute in 1 and 2,
We subbed in 0 and 0.5.
No, when we substituted
Oh yeah, I just made up a couple of numbers to substitute in. Yeah, I think we did 0.5 and 1. I don't think we can find the length of the spring from this information because I think there are a lot of springs that have the function 12x as the force function, and that's all the information that we have here really. So I don't think we can calculate the spring's length. Okay, let's get some units in here. So the units for work are, well, we just have to look at the units from this piece. What were the units for the 12x? That was newtons. Delta x, meters. And so when we multiply them, we find our SI unit for work. It's Newton meters. But apparently work is important enough to have its own unit. So what's the name of a Newton meter? That's a joule. So joule is the standard unit for work. There is like a British version for work that we'll see when we get to, there's an example coming up with pounds in it, but joules is the standard. All right, so number 3, I think kind of concludes this example. Go ahead, Richard.
Force f of x is given as a function of position x, and the work done in moving from x equals a to x equals b is given by a formula w equals integral a to b of f of x.
Okay, thank you. So that's exactly what we did, right? We just integrated the f of x function, the force function. Easy. All right, we'll come up here to Cole for number 5. Sorry, number 4.
Note that we get a physics formula for free. We've already seen Hooke's law, which requires a string by x meters. Equilibrium is.
Okay, so Hooke's law, anybody know it? Just oh, have we not seen? Does that not come up in the physics class?
Sure, I just can't remember. I know when we did
Right. I think, so I was kind of counting on you guys to know this, which is why I didn't bother learning it, but I think it's just saying that the force required to compress a spring is proportional to the position you are on the spring. For any given spring, the K might change, but each spring has its own value of K. If the spring is really tight, then K is high. There's a lot of force required to compress the spring. If it's a loose spring, then K is closer to 0. But I think that right there is Hooke's law. So then if we want to find, and what we did is just an example of that 12x was our formula for the force. So the work done to compress a spring is given by the integral of. So again, if we just look at what we had right up here, all we do is throw the force function into an integral and then stick a dx at the end. So I will throw the force function right here, kx dx. And then we'll go ahead and integrate that. Good. 1/2 kx squared, right? Yeah, make sure you're clear on which the variable is and which the constant is. And then technically a plus c, but in reality we would always be plugging numbers in and subtracting. But 1/2 kx squared, is that a formula that folks have memorized? Have we seen it? Right. So I guess I mean this doesn't give you anything if you haven't seen these two formulas, but if you have seen Hooke's law that the force required is kx, and you have seen this other formula that the work is 1/2 kx squared, they are two sides of the same coin, right? As soon as you understand why an integral is the right tool, getting from one formula to the other is easy. Okay, so just give me a sense for my personal knowledge. Is that a connection that's helpful to folks? Is that something we're interested in, or is it just whatever? Yeah. So yeah, so I think Maggie and Bubba are making a good connection here. A lot of formulas in physics are 1/2 something squared. And where did that come from? It came from an integral. Okay, good. All right, we're going to 5, over to Ernie.
We'll often look at work done by moving something opposed by gravity, standard gravity squared, force by pounds are up or a measure force.
Okay, so sometimes we're going to already be in force units, and sometimes we'll have to convert into force units. It depends on whether you're given the mass or the weight of the thing. So we'll see examples of each one. First, a very quick example of working against gravity. Number 6, Josiah. Okay, so we know that the work is what times what? Force times distance. This is essentially the only thing that I know about work. So work is force times distance. Now I have a distance here, it's 1.5 meters, but do I have a force? That 36, is it a force? What is the 36? 36 is a mass, right? And so I need to somehow come up with a way to rewrite the force in terms of the mass. And what is the famous force equation? Mass times acceleration. So, so then we're going to stick that down here. Force becomes mass times acceleration. And now all of a sudden work is MAD, mass times acceleration times distance, okay? So we will go ahead and start filling in the numbers now. So the distance is easy, that's 1.5 meters. The acceleration, we are fighting against gravity, so what's the acceleration of gravity? 9.8. I'm going to include units. Generally I don't, but we'll put them here. 9.8 meters per second squared. Yeah, and it's tempting to just throw in 36 for the mass, but grams is not the standard unit for mass. What is it? It's kilograms. So we're going to change that right away. So what is it? Everybody okay with that conversion? So kilo is 1,000, so move it over 3 decimal places. So that 0.036 kilograms goes right in here. Okay, and if somebody could give us a decimal. Okay, so 0.53, and you can check all of the units, and if you know your units, you'll see Newton meters, which is also, again, joules, but the only reason I wanted to throw units in there was just so we would start to think about converting the grams to kilograms. That's it. Okay, questions on that one? Why was that easy? Why was that not calculus? What was constant? Acceleration is constant. So the force required to lift this thing was a constant force. But if, for example, instead of being an eraser, it was, say, a bucket of sand, and there were a hole in the bottom of the bucket of sand, as I lift up, what would happen? It would get easier and easier to lift. This is now a calculus problem because the force required would be changing based on how much sand is in the bucket. So we're going to do something similar to that here in number 7. We're back to Andrew. Okay, so let's try this one, but before we do, let me just correct this this announcement over here. It says skip number 14, which as you saw was not assigned and also is not the one I want you to skip anyway. So we'll fix it. Skip number 18, which also is not assigned. So apparently I was on the ball and took the problem out of the assignment, but didn't realize I was on ball and threw it here. So don't worry about skipping anything because it's not assigned. Okay, so let's try Andrew's problem here. So we've got what's flat? The bucket, is it flat? There's 30 feet of rope, yes. Yeah. Oh, I understand. Yeah, if the bucket is like 8 feet tall, then that takes away some of the distance we have to cover it. Yeah, good. That's a very good point. We'll assume the bucket has like no height at all, but of course I'm going to draw it so that we can see it. Okay, so there's our bucket. And it's inside of a well, and so we're gonna have a rope attached to that bucket there, and it's gonna come up, and it's gonna come curve over. Maybe we've got a pulley here. We'll do all kinds of physics stuff today. Okay, so what's that? Does it?
It goes around another one, right?
I'm not, yeah, I'm just with one pulley, or do I need two pulleys to
There's two pulleys, right?
the compound thing? Wait, a single pulley, I'm going to say this on the record, which is bad news because I have no idea what I'm saying, but a single pulley doesn't make it any easier, does it?
Use your own weight to pull something down.
I'm not pulling down, I'm pulling.
Yeah.
Yeah, you can put down. Transfer it. Right, you could pull down.
Okay, so pulley is not a good thing to draw in here.
Yeah, no, it's the pulleys that have like two hooks, right? And the rope is actually.
Yeah, that's when you're moving more rope.
Yeah. I feel like it, yeah.
It's easier, yeah.
Right, right. And in this case, I'm not going down. We're just going straight. So even though I've translated this to a pulling horizontal, I still have to fight the gravity. I mean, it doesn't get any lighter. Yeah, okay, so I think we're good. Plus, it gives me a chance to draw my style in pulley. So what do we have here? So I'm going to mark the well. So the well is 30 feet deep, and I'm going to assume that the bucket is up a little bit off the well. So I'm already kind of pulling it up to some generic point. All right, so it's not at the bottom anymore. It's someplace in the middle of the well. And it feels like I should have a variable to tell me how high I've already pulled it. So I'm going to call x the distance that the bucket is, some generic distance from the bottom of the well. Because where that bucket is completely determines how much rope is left there, how heavy the remaining rope is. Now I arbitrarily chose to call x the distance I've already pulled. What else could you call x? The remaining distance that you're going to pull, and it's perfectly fine. So this is not the only choice. I'm making a choice, but there are other choices that are okay. And so we're then going to take the bucket and find the amount of work done in lifting the bucket like an inch or a tenth of an inch or just really some tiny sliver of a thing. So then let's go ahead and assume, or let's go ahead and calculate how much work we're going to do raising the bucket delta x. All right. And every inch I pull, why does it become easier to pull the next inch? Because there's less rope that's pulling this thing down. But, you know, from 1 inch to the next is not that big a deal. 30 feet of rope, that's going to be kind of heavy for us all together, but we're going to cut it into a little tiny thing so that basically the weight of the bucket is almost constant over this little tiny interval. All right, so let's start calculating. Again, the only thing I know, work is force times distance. Okay, I am going to make a change of symbol here. Instead of force, so we knew that force was MA, but I think we also know formula for weight. What's the formula for weight? Mass times gravity, right? Weight is mg. And weight and force are exactly the same thing, right? So I'd like to just call it W, but I'm going to write out the word weight because W is already standing for work. So force times distance, exactly the same thing as weight times distance. And in this case, I don't think there's any other translating to do. We're not going to bring the 9.8 in here. 9.8 was the acceleration for gravity. Weight is given to us. It's, what is it? It's a 50-pound bucket. This right here is already a weight. Or said another way, it's already a force. Okay, so we don't need to convert it. We don't need to do mass times acceleration like we did before. Everybody see the difference? I mean, you kind of have to know your units to understand this difference. 36 grams, that is a mass. We need to convert that to a force. 50 pounds is a force. How many people have not taken physics yet? All right, you folks are you are at a slight disadvantage at this point. So if there's stuff that I'm saying that we need to fill in like after class or something like that, then we should.
What is the unit for mass?
In the stupid version, I don't know. Anybody know the? So 50 pounds is the force, but what's the mass unit? No unit for mass? There must be. Yeah, there's like slugs and it doesn't make any sense. I think moles.
Moles is like that. So
Yeah.
Yeah, that's just a comparative.
All right, so I think we're good here. So let's go ahead and find the work done in moving over our tiny interval. Okay, so first we're going to do the distance. That's the easier part. What is the distance? What's the name we're giving to this tiny distance? Delta x. So that part is right there. This part is the trickier part, the weight. And why is it tricky? Because it changes. The weight depends on how much bucket, how far you've pulled the bucket up already. So what's always the same in terms of the weight of this contraption is the 50. It's always 50 pounds, right? Plus 50 plus. And then this is the slightly tricky part because the amount of rope that's left out there is dependent on X. So how many feet of rope are left here in purple? Is 30 minus X, right? 30 minus X. And we're assuming delta X is so small that it's not going to contribute anything. That's the idea. Yeah. So 30 minus X, that's how much rope is left. How heavy is each foot of rope? Is half a pound. So we need to do half a pound times 30 minus X. Everything else is going to be easy. Are there any questions on that calculation? Just for practice, let's get some more units in here. What are the units for the 50? So that's 50 pounds. What are the units for the half? It's pounds per foot. I'm going to write that. Pounds per foot. Great. What are the units for 30 minus X? That was the amount of rope, the purple. That's feet. So what happens with those units there? We just get pounds and then plus pounds. So in the parentheses there is pounds. And then that whole thing is getting multiplied by delta X. What are the units there? Feet. So all of a sudden now we have our stupid version for work, which is what? Pound feet, which I think most people say it in that order, foot pounds. And I haven't seen another name for that. Like Newton meters is a joule. I have not seen a name for foot pounds. So at least that's a good thing. I haven't named the stupid thing with another stupid name. I don't know why I'm so angry about this morning, but yes, which is stupid. Yeah. All right, so we've got that. That's fine and good. Okay, so then that right there is how much work is done for the tiny interval. What do we do to find all the work? We add up all those intervals and then we'll just jump to our integral right here. So the work total is equal to an integral. We're just going to copy that whole expression in black. 50 plus a half, 30 minus X. Delta X becomes dx. So yeah, it's a good question. What does X, how much is X, on the two different extremes? So how much is X when we start this process? 0, right? I start here and then ending at 30. So I'm going 0 to 30. So Joe, what did you suggest? Negative 30. So if so negative 30 to 0. So what you're doing is you're defining the bottom to be negative 30 and the top to be 0. If we wanted to do what Joe is suggesting, calling negative 30 the bottom and 0 ground level, which is perfectly reasonable, I think we would need to tweak the 30 minus x, because that's supposed to be a distance. And Joe, how much is your x at the very bottom? Is negative 30, and so 30 minus negative 30 is 60, and nothing in here is 60 feet long. So we would need to change that, but I'm certain we could, and then your limits would be good. Okay, anybody have a number for us? Okay, so while we're waiting for people to type in the calculator, let's do the non-calculus way to answer this question. So there is a non-calculus way here. Let's separate the bucket from the rope. The bucket weighs 50 pounds. The bucket is traveling how far? 30 feet. What do I do to those two numbers to find work? Multiply, force times distance. So currently we've got, so here's our don't tell anybody non-calculus way. Calculus. So we're doing the 50 pounds times the 30 feet. So right now we've got 1,500 foot-pounds. And then separately, we're going to add in the work from the rope. Now, the difficulty with the rope is that every inch that you pull is a different amount of work than the previous inch. However, we could kind of play the game that we played last class where we found, remember the bucket of muddy water? And we found the average density of this muddy water and then just treated all the water like that. So can we find the average distance that every molecule of rope is going to travel? How much distance is the average molecule of rope going to travel? It's 15 feet. The whole thing is 30. So on average, molecule of rope is traveling 15 feet. And I think we could take all of the weight of this rope and just hang it in a single point 15 feet from the ground level. So let's figure out how much the whole rope weighs. It's half a pound per foot. How much does the whole rope weigh? 15 pounds. And I'm going to compress all of the rope 15 pounds worth at the average distance, which is 15 feet away. So it's a 15-pound thing going 15 feet. What do I do with those numbers? Multiply them. Am I wrong? I think this is right. Yeah, all of the rope is 15. Well, there's an easy way to check. I'm saying, I hope the answer is 1725. What did we get on the calculator? Okay, good. So we did it right. But again, this is only easy because the rope was uniform, right? It was a 1/4 pound per foot everywhere. But if the rope were getting thicker towards the bottom and thinner towards the top, it would be very difficult to, to just kind of find this average, let's put all the rope at some average spot. It would be hard to do that. Any questions on this? So this is 1725 foot-pounds. Okay, so that's good. That's how much work we do there. And now let's come out here to number 8. This question will help on the project. Maggie. Okay, so let's give this a shot.
What's the density of water?
Am I wrong?
I just don't think a meter water. Meter, that's what right for. Okay, you're right. Really?
Does it seem too big to you? But water is surprisingly heavy.
Think about a meter cube water.
Yeah, and like a gallon of milk, for example, like how much does a gallon weigh? A gallon of milk? I don't know, but just ballpark. How much? I heard 5 pounds. I was going to say 3. I mean, like it's not insignificant, right? And then think about how many gallons you could fit inside of a cubic meter of stuff. There's a lot of gallons that you can fit in there. Yeah, yeah, but it's surprising how heavy water is, which is why, for example, like surfing can be really dangerous, right? I mean, like if you've been in the waves, it does not take very much to push you over, right? So it's because water is so heavy. Because when you fill the bathtub with water, right? Yeah. Good. Okay. All right. So let's see if we can do this one. So we've got our cylindrical tank. So let's go ahead and draw our cylindrical tank. And then we'll go ahead and start filling in some of the dimensions of our cylindrical tank. So let's see, it says it's 6 meters high. So the whole thing is 6. And the radius is 2. And then it says the tank is half filled with water. So we'll go ahead and fill the tank at the halfway point, which means it's 3 from bottom to the water level. And the reason that I like problems like this is that we cannot just dive into an integral and just say, okay, we're just going to integrate and then say blah. Like I think we really need to figure out why this is an integral. Every molecule of water in here, so again, work is force times distance. The force required to move a water molecule, does it depend on which water molecule it is? No, the water molecules all weigh exactly the same thing, right? So what's going to change is the distance, right? The water molecules in here are not all traveling the same distance. So here we need to make an adjustment because it's the distance that's changing. That's quite different than the rope example. What was changing for the rope every time you pulled it a little bit was the weight, right? It was the weight that was changing. Here the weight is the same, but the distance is changing. So how about instead of looking at each molecule, we try to group the molecules of water that are traveling the same distance. So we're going to slice this thing. Would you like to slice it vertically or horizontally? Let's slice it horizontally, because if you just slice through here horizontally, all of the molecules in that circle are traveling exactly the same distance straight up. So let's draw our slice. And in theory, we're going to make that like a razor thin slice, but I'm going to give it some visible thickness here just so we can do our calculations. So we've got a little thin slice. What would be, okay, so let's come up with a variable here. What characteristic about the water in that slice determines how far it has to go to get to the top? Is its position. So what would be a good place to put an X? Yeah, so the distance up and down, say from the bottom of the tank to wherever this thing is. So I'm going to say X is that distance right in there. And again, just as well, you could call X the remaining distance it has to travel. Either way is fine. And how about the thickness of the slab? Let's call that a delta X. It's going to become our dx. Okay, so I think we've got stuff set up. Let's start doing our calculation. Again, the only thing I know about work is force times distance. That's it. You guys know the old time telescopes that kind of expand? You know, it's like this real tiny thing, but then it gets bigger, bigger, like ship captains used to have them. Right, so that's what's about to happen with this thing. Force times distance is two little things multiplied together. It's about to expand to some more things, but we're just going to use first principles. The force. We're trying to pull against gravity here, right? So it seems like we're gonna need to do that kind of conversion that we did before. Instead of force, what can we put? Force equals mass times acceleration, or weight. Either way is okay. So I'm going to put here mass times acceleration times distance. And part of the tricky thing here is that the mass is not really given. It doesn't say how much water weighs per se. It gives the density of the water, right? 1,000 kilograms per cubic meter. So what do we need to do to calculate the mass? I need a volume, right? The mass of that slab of water is going to be its volume times the density of water. Volume times density. So this is equal to mass now is equal to volume times, and again, I know you guys used rho in your physics class. I think the book uses little delta, so I'm going to use little delta. And then times acceleration times distance. Okay, and then one last thing, and we're done with this stage. The volume of that slab. So I'll put a subscript here. This is the work done for the slab of water. What kind of a shape is that slab of water? That's a little cylinder. What's the formula for the volume of a little cylinder? Pi r squared h. So the volume is now here, and I'm copying everything else. Delta, acceleration, distance. Any questions on any of those pieces? What's a delta for density? I'll put it up here. Okay, so force times distance expanded to all of that stuff because the force was quite a complicated thing to calculate in this case. But I think we've got all the pieces now, so let's start throwing in the actual numbers from our example. So this equals, oh, and drawing that symbol just reminds me that some of you are very opposed to drawing equal signs on your quizzes and projects and things like that. You're just very stingy with the equal signs. I don't know if you feel like you're paying like per equal sign or something, but a lot of times on quizzes and tests, we'll have, so let's fill in the next one and we won't put the equal sign, and I'll tell you what I don't like about it. So I'm going to copy all that stuff. So we've got a pi for this slab, radius is 2. It's the same for all the slabs. So that's going to be 2 squared times. And let me point out, even if it weren't a nice cylinder like this, what if it were something that kind of came in, like maybe it was a cone-shaped type thing. Okay, I can calculate the new radius. It's going to be a changing thing, so it'll have x in it. But really, we could handle very complicated shapes. It's a cylinder, but we could handle more. Okay, pi r squared h. The h is the height of the slab, delta x, times the density, delta. And it's given in the problem. It's the density of water is 1,000 kilograms per cubic meter. And we'll go ahead and I'll just write a couple of the units here. This was kilograms per cubic meter. This thing right here was a volume. What were the units? is cubic meters for the volume, right? So right there, I've got kilograms. Okay, we are continuing to fill in the blanks here. So right now we're up to this guy. The only reason there's work to be done here is because gravity is trying to keep the water where it is and we're fighting against it. So A is 9.8. And then finally the distance. And really this thing is the only reason we had to use calculus, is because the distance depends on where the slab of water is. So X was the name we gave to how far it is from the bottom. We're trying to get it to the top. How far does it have to go? 6 minus X. Is that okay? The green slab is already X away and it needs to get to the top, which is 6. 6 minus X. And that is meters. So to crunch the units together, you'll find Newton meters when all is said and done, which is good. And I think that's it. We're done. We've got our formula. That's the work done for one little slab. What's the next step? Before integrate, what's the next step? There's a summation of all the little slabs, right? And then that becomes the integral. So we'll just put integral of all that stuff. Yes, and that's going to come up where in the integral? The limits, right? The 0 and 3 only comes up with the limits. So we've got integral from 0 to 3 of all that stuff. Pi 2 squared 1000 9.8 6 minus x. Delta x I'll stick at the end as the dx. The force that we're applying is positive. Good question. Yes, the acceleration is negative. Okay, so somebody can type that integral in. It's actually a very easy integral without typing it in, but let's just get a decimal from the calculator. And while we've got, okay, nobody typing it. Oh, one person is typing it into the calculator. How much? 10 to the 6th. Confirmed. Okay. 1.66 times 10 to the 6th. And we're in SI, so Newton meters or joules. And that is how much work is required to lift all that water. An enormous number, as Cole points out. Water is really heavy. A lot of work. Again, there's an easy way to, oh, I used a symbol there. We're trying to avoid using the symbols. So there is an easy way. Oh, Chris.
So when it says how much work would it take to pump it all to the top? What does that mean?
So you've got we're lifting the water, and so if you could go in there with but it's actually difficult to do in practice and have that be the right answer. If you have, yeah, if there were like some kind of if a piston could push the water up, that would be the right answer. But in practice, you know, you've got like this big tube that you stick in the tank and suck it all up. Where do you put the opening of the tube? Probably at the bottom. What does that do to the work? It increases it. It means that all the water is going to go the big distance.
Yeah, like the way pumps work, I don't think it matters the circumference of the.
No, I don't think that would matter. Yeah. Would it? Would we gain back? So you're saying maybe if we've got our tube here and it goes to the bottom of the tank, the water that we first pull out, Sam, I think is suggesting that that water is going to be easier to pull out because you've got other water around the tube kind of pushing down. Yeah. So then maybe it is an okay answer, based on the other water helping. Well, we are going to pay for it in that the water that was only 3 feet from, or 3 meters from the top is now going to be further by the time it gets down to the bottom. So like it's helping us.
Right, but where did that energy go? It's not going pressure.
I think Sam is saying it is pressuring the tube to make the first. Yeah.
I agree with that.
Yeah. Okay. Wait. So who are you disagreeing with? Did I say something you're disagreeing with?
I don't know, maybe.
Okay. Okay. So that is the answer. And again, there is a non-calculus way to do this. What you could do is assume that all the water is at the average water distance. So where could we compress all the water? Is to the 1.5 meter mark. And you could just take all the water and put it right there, make it one little drop of very compressed water. So find the volume of the entire tank, pi r squared h. Find the mass of the entire tank by multiplying by the 1,000, and then just have it travel 4.5 meters. And so without any calculus, without any slicing, without any integrals, we'll get exactly that same answer. But again, it's only easy because it's easy to tell what the average distance is that the water has to move. Okay, so what I don't like about this is that it's not clear what this line here has to do with any of this stuff. And it doesn't take much to make that connection. What does it take? It takes an equal sign. But the problem is if you don't put an equal sign there and you don't put an equal sign on the last one, are these two guys the same thing? Not. What does the first line here represent? The work for what? A single individual slab. That's what that thing is. What does the integral do? It gives you all of the slabs, but they're not the same. So if you don't use equals, like it's really difficult because there should be equals in some places here, but not others. And if you just consistently don't use any, then it's really hard for the reader to decide, okay, is this equal to the previous line, or is this a new thought that we're starting with? So I would encourage you, I have encouraged folks on quizzes and tests, I'll write down, lots of equal signs. I feel like I'm using more than my lifetime allotted equals signs. So if you could start putting equal signs in, that would be good. So that's that. And then how about we say over here the total work, just so that we make it clear this is a new calculation, a new thought. Certainly it's related to the previous thought, but the total work is that guy. And then that is approximately 1.66 times 10 to the 6th.
Are we allowed to put extra?
If you put equals in something not equal, that's a problem. Oh, 2 equal signs. Yeah, some people do need to kind of make up for their lack of equal signs in the past. All right, now we do get to answer a related question very easily now. I think we're at Dawn. So just change that 6 to a 5 because there's already a 6 in the problem. 5 meters above the tank. So we're not just bringing it to the top of the tank. We're moving it to 5 meters above the tank. Yeah. So then the distance that the water has to travel is now not 6 minus x. It's 11 minus x. So how would the formula change? Work total equals integral 11 minus x dx. How about the 0 and the 3? Still the same. Okay. So once you've done the work, it's very easy to then move the water to any point that you want to. And don't be concerned about horizontal movement, like like with the hose. If we just stick this giant tube in here, like the water will all end up like coming up to a spot right there. So some water just goes straight up to that spot, but other water has to go like off at an angle. It feels like it's going more distance, but part of that distance is horizontal. We've already decided that work horizontally means nothing, right? We don't do anything to move the water horizontally. So it only counts as work for the straight up. So it makes no difference whether things are kind of concentrated at one spot and has to move horizontally. It's totally fine. Okay, so that is good. On the next page, there's a challenge question. We have 9 minutes left. Here's my recommendation. Either jump into the homework assignment, or maybe double check your chocolate stuff with your neighbors here, or if you haven't finished the chocolate stuff, this is 9 minutes you can chat with your neighbors about the chocolate stuff, or you can get started on project number 3, and in particular, question number 1 is very relevant to the stuff we just did.
Project number 3,
By project 3, I mean project 6. Thank you.